Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. This is tutorial 6, which is the last tutorial for sections under kinematics of rigid bodies, which will cover the relative motion analysis using rotating coordinate system. Okay, so we'll look at the first example here. At the instant shown, ball B is rolling along the slot in the disc with a velocity of 600 millimeter per second and acceleration of 150 millimeter per second square, both measured relative to the disc and directed away from O. At the same instant, the disc is rotating with angular velocity and acceleration as shown. Determine the velocity and acceleration of the ball B. So here is the ball. Here's the ball B, and this ball is rolling away from O outwards, okay, in the direction of X. And the question has already selected their coordinate system XY, and then it is moving at a velocity of 600 millimeter per second and acceleration of 150 millimeter per second square away from O, meaning the direction is positive X. At the same time, the disc is rotating at 6 radian per second and accelerating in 3 radian per second square. And if you can see, the direction is it is in the positive Z, so the unit vector is in the positive K direction. So these are the data that we capture from this analysis. Look at the data. What do we have? So we can see that the XY axis is rotating. So the XY axis is sort of fixed to the disc. It follows the disc. So it is a rotating axis, and the speed or the angular speed or the angular velocity is 6 k radian per second, and the angular acceleration is 3k radian per second square. Let me write the unit here. So it's a 3k radian per second square. Sometimes if I have the space, we can write the unit. So, and then what else do we have? We also know, this is the thing that we usually do. We just pick up the points. For example, we know that the position vector of B relative to O here is 0.4 I. It is 0.4 meter away from O. So we know that position vector of B is 400 I. And the velocity of B relative to O is 600 I millimeter per second, or and also the acceleration of B relative to O. This is the acceleration of the ball in the slot moving away. And I put an A here. The reason I put an A here, because you usually reserve O for the big capital XY. So now I'm using the small for the small axis, the rotating axis, I put A as the origin. So maybe I would write to put there. So I put A as the origin of X, Y, whereas O is origin of big capital letter X, Y, the global and the local coordinate. So then I can find the velocity of B relative to A 600 I, and this is acceleration is 150 million. So I know that from this fact that the origin of the XY axis, i.e. point A, does not have linear velocity and acceleration. So the velocity of A and the acceleration of A equals to 0. Remember our equation? So we can write down the velocity equation. VB equals to VA plus omega cross position vector B relative to O. This is now, it can be written also as position vector B relative to A, similar. So plus VB measured from the rotating axis. So this is our relative velocity. So velocity measured relative to XY. So here VA is 0. We know that VA is 0. So I put here VA is 0. We know that omega is 6K. Omega is 6K. And position vector is 400. It's 0.4 meter. So that's position vector. And I know that my acceleration is 600 millimeter per second, or the velocity is 600 millimeter per second. So this is 600 millimeter per second. And therefore, we get the answer 2400 J plus 600 I millimeter per second. Just in case you can't see it, so I'm rewriting it. So it's equal to 2400 J plus 600 I millimeter per second. So that's the answer to the question. Okay, so we need to find the acceleration equation. So for the acceleration equation, we have AB. There are 5 terms. Yeah, AB equals to AA plus omega dot cross position vector B relative to A to omega cross VB relative to A minus omega square R B relative to A plus the relative acceleration. I put an A here just in case that A is also the same point, but A belongs to XY. Yeah, so we know that AA is 0 from the previous slides. We know A is not moving. Okay, so A is not moving. And omega dot is 3K radian per second squared times 400 I. This is position vector B relative to A plus 2 omega 6K cross 600 I. That's the relative velocity minus omega square 6 square 400 I is the position vector, and finally the relative acceleration is 150 I. So you got that 1200 J plus 7200 J minus 14,400 I plus 150 I, and that's your final answer, 8,400 J minus 14,250 I. So this is somewhat a direct application for the system. So it is always the case that students would ask me, how do I know, for example, from this big equation here, from this long acceleration equation here, how do I know which one belongs to which? Yeah. So this is the way that you have to understand how the system is working. Let's look at. I'm going to explain a little bit for those who cannot remember. Something like this is your rotating XY axis, yeah. And remember, it rotates. The system, you are rotating at a speed of omega, and also there is a angular acceleration. And you got this point B here, and this is point A is the axis, the origin of your axis, and then you got the big capital XY. Okay, and this particle is moving, so the equation is, this is O. Just give it to Y. So when we write down VB for this coordinate system, VB is measured like VA plus omega cross position vector B relative to A, yeah, plus velocity B relative to A measured in the XY axis. These are the big formula. So when you look at this formula, for example, when you look at this formula, the issue is how are you going to apply. So you remember, VB is the actual or absolute velocity of B. So VB is the absolute velocity of B. So this is the absolute velocity of B. VA is the speed of the origin. So omega is how fast rotating axis is moving, or angular velocity of the rotating axis. Vector B relative to A is position B relative to the coordinate system A, and V B relative to A is the relative velocity of B measured in the XY axis. So this is the fundamental of, if you understand this, you'll be able. So when you look at the problems here, for example, I'm just highlighting this. It doesn't seem like as though I'm highlighting it. So when you look at this system, yeah, so you know B is here, and you know A is somewhere here, okay, and you must know what is the velocity of B and what is the velocity of A. So A is not moving, so you can say that, oh, A is not moving because it's on the axis, it's just rotating, so VA is 0. So you can put it, okay, 0. What is omega? You know your omega. Omega is 6 radian per second. Is given. You know your position vector B relative to A. This is given. And then you know your final velocity. It's given here. Your velocity relative is 600 mm per second. So it's all about understanding the terms. I hope I've explained it quite clear. So let's look at the second example. Here is a similar example, just to reinforce your understanding on the subject. Figure below shows a collar A sliding along the arm OB, sorry. There is an arm. So you've got this arm OB, and you've got this sliding, a slider which is sliding along the arm OB, such that the velocity and acceleration measured relative to the arm are 5 meter per second, is given here, 5 meter per second, and 3 meter per second square correspondingly. So at the same time, the arm is rotating with angular velocity of 3 radian per second and angular acceleration of 5 radian per second. Determine the velocity and acceleration of the collar at the given instant. Okay, so let's look at this statement and see whether we can read out some data. Okay, so the figure below shows a collar sliding along such that that the velocity and acceleration measured relative to the arm. So this 5 meter per second and 3 meter per second square. What are these? These are our relative velocity. So we can label that. We can label that as V, B relative to A in the XY axis. I'm talking about referring to the previous notes, yeah? The where the B and A are the points on the, so this 3 meter per second square, these are the relative acceleration. So okay, but in this instance, VB relative to A is actually A is moving, so we need to look at our system, and we said, okay, now for this is our notes. Let's say this is the notes that we have. Okay, so in our actual application here, it is relative velocity of A, VA relative to O or P, and that's in the small xy direction. So similarly, here is the notes. If you look at the question here, so our acceleration is acceleration of A relative to P or O in the small xy. Right? At the same time, the arm is rotating with angular velocity 3 radian per second. So again, we have this 3 radian per second. Yeah. And then angular acceleration of 5 radian per second square. We know that this belongs to this data because of the coordinate system xy. Our coordinate system xy is pinned or fixed to the rotating arm, so it's also rotating in the direction given. So this is our omega dot. The 5 radian per second is our omega dot, and this 3 radian per second is our omega. And it says here, determine the velocity and acceleration of collar at the given instant. So in this case, we know that the origin of the small xy axis is not moving. It's only rotating. So I put it here, the origin of xy axis at P does not have linear velocity and linear acceleration. So Vp equals to 0, Ap equals to 0. So in the notes, this will be, if in the notes, I keep on coming. So in the notes, it will be VA equals to 0 and AA equals to 0. This is for the from the notes. So let me pop and then let me highlight this. This is only from the notes. Okay, so we can rewrite the velocity equation. We can rewrite the velocity equation using our current system. So VA, which is the velocity of the collar, and Vp is the origin, plus omega. Omega is the rotating speed of the coordinate system, cross position vector A relative to P. This is also given 2 meters here, plus the relative velocity. So it is 0 plus 3k. We know that it's rotating in the positive k direction, cross 2i plus 5i. So the answer is 6j plus 5i. So that's the answer. So using the same approach, we can now apply the data to the acceleration. So when you look at the acceleration, I have written down the long acceleration equation. AA equals to AP plus omega dot cross position vector A relative to P plus 2 omega cross relative velocity and minus omega square position A relative to P plus the relative acceleration. So that's why in the beginning, we have already identified which is omega dot, which is omega, where is the relative acceleration and the relative velocity. So we know that, as our analysis show, that the xy axis is not having any linear acceleration. So AP equals to 0. What is the omega dot? Omega dot is 5k. It's a positive k direction moving, and is given here as 5. It's 5k cross the position vector is 2i known, plus 2 omega. Omega is 3k. Position vector, the relative velocity is 5i. We know that is given here. And then minus omega square, 3 square, times 2i, position vector, plus the relative velocity 3i. And when you do the calculation, you will have your answer here is 10j plus 30j minus 18i plus 3i equals to 40j minus 15i. So that's the answer to this. So the whole exercise of 1 and the exercise of 2, question 1 and question 2, is just to identify from the problems here what are the data which belongs to which parts of the equation, which parameters of the equation that it will be used in the calculation of the velocity and the acceleration of the collar or the wall, as in the first question. Yeah. So I hope that is much clearer to you on how we have obtained this one. Yeah. So I just want to again show to you how we relate this to. So if you look at our XY system, so the XY system is here. I'm going to highlight this XY system in yellow. So this is our XY system. Okay. And it is rotating. So it's rotating, shown here. It is rotating. And the origin is sharing the same origin as, shares the same origin as O. Yeah. So that if you can put a similar analysis to the, so initially what we have is we have a rotating axis XY. I'm going back to the notes here. I've got rotating axis XY. Okay. omega and omega dot, and then you got point B, and this is point A, and then we have got point O. So this is our X, Y, and O. Yeah, and this is position vector B relative to A. So if we apply this system to our current coordinate system, it will say that O and A overlaps. Yeah, here O and P overlaps. Yes. So the equivalent, if you use the nodes as our nomenclature, it will look like this. So if the global coordinate axis is in blue, X, Y, and O, the rotating coordinate system is in red, for example. So you've got your X and Y. Whereas XY axis is fixed, this guy is moving. Omega and omega dot. And where is B? B is here. And this is you can write that as position B, vector position B, relative to A. Where is A? A is coincident with O. So the red one belongs to the rotating axis. Yeah, so that means that in this case, what happened is that in this case, position vector A relative to O, in this case, position A relative to O equals to position A, vector position A, becomes 0. They are I dot E because of point A and O, points A and R on the same, are at the same place, at the same coordinate. Okay, so that is what happened to the current system. You'll see the same system happen in tutorial question number 1 also. Yeah, so this is what actually happened to the system when we apply that. So therefore, when we write this kind of equation, yeah, so initially the equation of B is equals to VA plus omega cross position B relative to A, B relative to A, plus velocity of B relative to A in the XY coordinates. So here is because VA is 0. Yeah. Similarly, plus, and it just becomes omega cross position vector B relative to A plus the relative velocity. Okay, so that's how we understand this system over here. You can do the same thing with acceleration, but the whole idea is to prove to you or to show to you what happens when OA is coincident compared to the case where O is separate from A. So, and this is the case which is being applied here. Yeah, so we go from this to here, and then we apply it to this case. So that's how we solve for number 2. And let's look at number 3. Question number 3 is about a color E. There's a color E. Should I color this color? So let me color that in yellow. So in yellow. Okay. So the color E is attached to and pivots about a rod AB. So you pin the collar E to the rod AB while it slides on rod CD. So E is free to slide around CD, but is pinned and pivoted about rod AB. If rod AB has angular velocity of 6 radian per second and angular acceleration of 1 radian per second square, both in the clockwise direction, so both are in the, so 1 radian per second and 6 radian per second, 1 radian per second square and 6 radian per second are in the clockwise direction. Determine the angular velocity and the angular acceleration of rod CD at the instant shown. Use the rotating coordinate system as indicated in the diagram. Okay, so here we have two rods, AB and CD, and we have a slider. That slider is pinned to AB, so that slider cannot move relative to the rod AB, but that slider is free to slide along CD. So you have, when you say it's free to slide, this slider E has a relative velocity to the rod CD, whereas AE, there is no the velocity, there's no relative velocity A and B, E on relative to AB. So at the same time, it's given here that AB is rotating 6 radian per second and accelerating at 1 radian per second square in the clockwise direction, and the angle of AB is 45 degrees to the horizon, and also angle CD is 45 degrees to the horizon. At the same time, the position is given because it's 45 degrees, and the location of ED is 4 meters and AE is also 4 meters. So you have got this 4 equal sides for the 45 degrees triangle. So the question asks us, how do we determine the angular velocity and the angular acceleration of rod CD at the instant shown? Okay, so let's look at the velocity equation. Can you write the velocity equation for the system? If you look at this, would you be able to write what is the velocity of, and it's given to you, the rotating axis is given here, x and y. Okay, so if you look at the velocity equation, what we are interested is VE can slide. Okay, this is our coordinate system, and the origin is at D. Does the origin move or not? So the origin doesn't move. So if the origin doesn't move, the velocity of the origin of the rotating coordinate system is 0, and the acceleration of the origin of the coordinate system xy is also 0. So here we have, you don't put anywhere yet. So, and then we have this 6 radian per second and the rotating arm in AB. So when I write down the velocity equation, it is the velocity of E equals to velocity of D. What is D here? Is the velocity of the origin of the rotating coordinate system. Okay, plus omega. What is omega? Omega is the angular velocity of the rotating coordinate system times position vector of what? Position vector of the object measured relative to the origin of the rotating coordinate system. So measure of object E measured to the origin of the relative coordinate, measured the object of E measured to the origin relative to the origin of the coordinate system, which is at D. And then we have the relative velocity V measured to the xy. Yeah, so because E can slide up and down, yeah, so can I put an arrow here? Let's put an arrow in a blue arrow showing that there is this VE relative to D in the xy axis. Okay, and I can also say that, okay, maybe I can also write, yeah, the acceleration also move in the slot. Dia tak boleh pergi mana-mana. So yeah, the acceleration also something like that. Yeah, so that's how. And then I wrote down here the acceleration equation. Acceleration equation, AE equals to AD plus omega dot cross position vector E relative to D plus 2 omega cross the velocity, relative velocity, minus omega squared plus times the position vector plus the relative acceleration. It's a lot of data that we need to put in. And let's look at the velocity equation. So from the data from question, omega, do we know what omega is? We don't know what omega is. So we can assume that omega equals to omega CDK. So we don't know what is the velocity, angular velocity of rod CD. What is omega dot? We also do not know. So we just replace that with alpha CDK. Okay. And then where do I label this? Where is this omega CD and alpha CD? It is the velocity. So I'm gonna take you here. This is this. So I am going to write down. So I'm gonna write down this omega and alpha CD. Yeah. What is the position of vector E relative to D? This is the position vector relative to the origin of the rotating coordinate system. So the origin of the rotating coordinate system is D. So now I wrote as is 4 meter from here to here, as these tiny blue things 4 meters. So I could put down position vector of E relative to D is 4J. What is the velocity of E relative to D? I do not know, but I know that the direction is in the J direction. So I say that the slider can move up and down, so it is in the direction of positive Y. So I can put it, the magnitude is V relative and the direction is J. So I put that VE relative to D, J. Similarly, I have shown you that what is the relative acceleration? No, I do not know what the relative acceleration. But slider E can move up and down these slides. And therefore, the relative acceleration of E relative to the origin is in the positive Y direction. Therefore, it's AE relative to D is in J direction. So, when you, so are we ready to, what about E? What about the velocity of E? Velocity of E, because E is pivoted on so we have the acceleration equation here. So we can calculate VE. VE because of pivoted, E is pivoted along the rod AB. Therefore, we have this minus 6K cross 4I. I know that point B will move together with rod AB. Okay, so that VE equals to omega AB cross position vector E relative to A. This is a fixed axis rotation about A. So the axis, the rotational speed is omega AB is minus 6K and cross position 4I. This is 4I. 4I is the direction. We have to use the rotating. So it's a 4I. 4I. So minus 24J meter per second. Do we know what? Similarly, we can calculate the acceleration of E. There are two components, the tangential component with alpha AB cross position vector R, E relative to A, and then the normal component is minus omega square AB times position vector E relative to A. Yeah. So here we can put in the value. Alpha we know is minus 1k. Position vector E relative to is 4i equals to 6 square. Omega square is 6 square times 4i. So we have got here the relative or the acceleration of point E is minus 4j minus 144i. The key here is to understand this is a fixed axis rotation. So I might want to write it down here. I said this is fixed axis rotation. Yeah, so point E rotates about A. Yeah, so E rotates about A because of the bar AB. Because of the bar AB is rotating about point A. So point E will only rotate about point A. So the velocity can be calculated using a fixed axis rotation. This is the velocity and also the acceleration. Yeah. So after that, it's just a matter of putting in the values that you can find from the questions. Okay. So let's say we put in all the values here. What else that we don't have? So look at the velocity. VE equals to VD plus omega cross position vector E relative to D plus the relative velocity. What is VE? We have calculated VE to be minus 24J. VD, the velocity of the origin is 0. Omega kita tak tahu, so we just replace omega with omega CDK. Position vector E relative to D is known is 4J. Yeah. And the relative velocity, we do not know, but we know the direction to be dalam arah Y, positive Y. So we said that somewhere here is VE relative to D in the J direction. And looking at the acceleration equation also, we can already apply some of the data that we have. Do you know what AE is? Yes, we have calculated AE because it's a fixed axis rotation of point E about A. So it's minus 4J minus 144I. Do you know what AD is? AD is the acceleration of the origin of the coordinate system. So we look at the coordinate system, point D doesn't go anywhere, it's fixed to that point, so AD equals to 0. Do you know what omega dot is? Omega dot, we don't know what omega dot is. We put here alpha CD, so we replace omega dot with alpha CDK. Do you know position vector? Yes, it's for J. 2 omega. Omega also, we do not know what omega, so we have substitute with omega as omega CDK. And then the relative velocity, we do not know what is the relative velocity, but we have substitute with, we know the direction is in the J direction, VE relative to D. Omega square, again, we do not know. We have put it as omega CD. And position vector we know, and alpha and the relative velocity, we do not know, but relative acceleration, sorry. The relative acceleration, acceleration of E relative to D in the rotating axis, we do not know that, but we know the direction to be in the positive J direction. This is how so when we are ready to substitute the value, if our understanding of this is correct, then we should have the correct answer. So for the velocity equation, this is the velocity equation. VE equals to VD plus omega cross position vector E relative to D plus the relative velocity. And then from the data listed in the previous slide, we know that VE is minus 24J, VD equals to 0, omega CD kita dah ganti dengan omega CD. So anyway, it's the same thing. It can also be written as omega CD. Yeah. So this one is also, I might have made some mistakes here. So omega CD K cross position vector for J plus the velocity we know is in the VE relative to D is in the J direction. So it's minus 24J minus 4 omega I plus ED relative to the relative velocity. So we can solve the pi parts, the I parts and the J parts. And we've solved the I parts, we will get that omega CD equals to 0. And for the J parts, VE relative to D is minus 24 meter per second. So that's the answer for the relative velocity. So the question to ask, what is the angular velocity of CD is 0. At the time given is 0. Doesn't mean doesn't move, but for that instant it is 0. So we can now move to the acceleration. So when you look at the acceleration, the long set of equation 2, from the data, listed data, we can substitute the values. So I've substituted the values. We have calculated AE to be minus 144I minus 4J, AD equals to 0, alpha CD K cross 4J, yeah, and plus 2. The omega is 0 from the previous answer, last slide, times the relative velocity in terms of J, and then it's minus 0 square cross, there is no, this is omega square. Again, this is omega, yeah, cross 4J plus the relative acceleration. So we have these terms, minus 145I minus 4J equals to 4 alpha CD, K cross J is minus I, so it's minus 4 alpha CDI plus the relative acceleration J. So we can solve this by parts, I and J. So it's here minus 144 equals minus 4. So we have alpha CD equals to 36 radian per second square. And also J equals to minus 4 equals to the relative acceleration. So the relative acceleration is minus 4J meter per second squared. So these are the answers to the question. I was a bit fast on the acceleration, but it's the same approach. Just look at the terms and we apply the terms. Luckily here that we have our velocity 2 omega 0, and minus omega square cross position vector E relative to D is 0. So we have got many 0 terms here, 1, 2, 3, 0. So maybe you have to highlight the 0 terms. The speed of the acceleration of the origin D is 0, and 2 omega cross position vector 0, and omega square is 0. So we have solved this equation. So I hope you can follow. If you carefully look at all the problems in the textbook, it looks the same. They just change the shape, and there is always a sliding motion relative to the rotating axis. So the key thing here is to select your rotating axis to be with the sliding motion. So maybe we should write down a lesson here. So select xy to be, i.e. xy is to be with the sliding motion. Okay, so I'm going to give a bit more explanation on this. Why?